There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our new direction of physics videos. So this is video 14. We're going to continue on our theory of self-interacting field theory. So in the last video we already compared the format of general relativity with electroweak interactions and Maxwell equation, Newton's law of gravity. We rewrite general relativity into a tensor format. Okay, compared with Einstein's general relativity, we are in a tensor format, much cleaner format. So the final equation of self-interacting general relativity, that means modified general relativity, it's a self-interacting version of general relativity, okay? To replace the traditional general relativity to overcome the compatibilities with other theories. Because for example, you have Maxwell equation, it's a tensor format, and also the Lagrangian, it's first order differential of the field variables, okay? But Einstein's field has second order differentiation, so they are not compatible. This is why last video we have the final equation. So this video we're going to talk about the new Schwarzschild solutions, which that's one of the most important solution for a static, spheric, symmetric object. So we can find the solutions. And then that's the Robertson-Walker metric. That's like cosmology. Okay, that's the classic test of general relativity. Okay. So we also talk about that Einstein's general relativity and my theory are different. The extra term I added into the equation, which by chance it's one of the extra terms is zero. Okay, so whatever Einstein's test have, it's proving the theory, and my theory also satisfies. Okay, so let's talk about the final equation we have. Okay, so because we define a field variable which is a difference tensor and a scalar. This is a scalar. Okay, this is a tensor. Okay, so this self-interacting field equations, it's like that. Okay, so if we expand the equation, we see that. Okay, if we expand that, so the difference what we have now, it's pretty simple. Okay, compared with general relativity, we have this term, that's the potential tensor. Okay, okay, that's a potential tensor. That's a new definition. Okay, new variables we're introducing into the self-interacting field theory. Because remember, when we have the Newton's self-interaction, Newton's law, we have phi, the square phi. I mean, that's the potential. But now we're going into the tensor version. Einstein's field doesn't have that. Okay, Einstein's general relativity doesn't have that. This tensor allows us to have a boundary, okay? Because on the boundary, this term goes equal zero on the boundary, okay? So we have another extra term. This term we call scalar, self-interacting term, okay? So the modified general relativity or the self-interacting general relativity has two differences. One, it has a boundary. Second one, it's a field will bend itself. That's an extra term. The rest is the same as general relativity. But that's what we're looking for, okay? So if we define the curvature tensor like that, that's slightly different from Einstein's, okay? And our gravitational constant, it's an integration of the whole boundary. So that's also the difference between the current Newton's law of gravity and the self-interacting field theory, okay? So the potential is 0 on all boundary surfaces. What's interesting is it's because in the Schwarzschild assumption, it's this assumption, it's spherical, okay, and static, okay. What it means, the variable only depends on r, and no t dependent. That means the variable doesn't vary with t, okay. The variable only varies with r, okay. So this is a very good solution to discuss, to compare the self-interacting general relativity, how it's different from the traditional Einstein's theory. Because in the static and spherical, d mu equals 0, okay? Because that's what we talked about in the previous video. Now you see the extra term we added, it's 0. So that means except this potential tensor, this term is automatically equal 0. So now we would like to see what's this contribution to the difference. What do we see that we gave two solutions? Because in the second video we already talked about when we introduce a self-interaction, we're introducing a nonlinear. We have two solutions in the self-interacting field theory. One large solution, one small solution. The large scale solution is for gravitation. The smaller scale solution is for strong interaction. Now we have this nonlinear term, okay? That's what we're introducing. Let's see what it has, okay? Because we defined a differential tensor, okay, from the Schwarzschild solutions, okay, what we have the difference tensor. This is now a tensor. Einstein's affine connection is not a tensor. This is a tensor, okay? We basically redo the tensor. We also have the Minkowski affine connections. What we defined, so basically we defined Einstein's r theta phi equals dr theta phi plus ida r theta phi, okay? So what we did in the previous video, we separate the geometry part, okay, with the gravitational caused by the matter, okay? So this is what we call gravitational. This gravitational, okay? Okay, this is metric part. So our equation is different from Einstein's. I kicked away. What we did, we kick away the geometry part, okay? The geometry. Okay, we kicked away that. So what we have is a difference tensor, okay? The difference tensor, what we wrote down over here, we have an extra term, okay, so here, so that's what we have. If we continue doing that, what I wrote it over here, the red terms, it's a difference between the self-interacting general relativity and Einstein's general relativity, okay? So, but this term equals 0, that's a difference, okay? If we do that, we do the solutions, okay? We find the potential tensor, okay, from those equations, okay? So the potential, since needs to be 0 on the boundary, if we take the potential tensor like that on the boundary where it's symmetric, okay? So what we have over here, it's like that. We see that if we have RTT and RR, this term equals 0, we have this something like that. We have two solutions now, okay? We have one solution. That's exactly Einstein's general relativity. Okay. General relativity. Okay. So that's that. Okay. That's exactly the same. Okay. We have A equals something like that. That's gravitation of r squared. We have a solution too, because if we by that, so we have another solution like that. Okay. This is a new solution. We substitute into the theta term what we got. We get a much stronger force. It's okay 1 times c over 3/8 of that. So which decrease faster, because as we r goes away from the radius, it's much faster, because compared with r over here, when we increase the r, okay, if we have a mass, we increase r, this potential decreases slower. This is much faster. So we see that that meets the property of strong interaction. It's much faster decrease. Okay, so that's what's interesting. This solution does give us two solutions. That means in the same equation we have two solutions. We have described two fields. Okay, basically we have a weak field like the universe. We have a stronger field but decrease very fast. That's like the nuclei. Okay, but the Schwarzschild solution in the nuclei, because it degrades so fast, we need spin or we need charge to really describe the protons, neutrons, and all those elemental particles. What we did is, if you watch the video from the beginning, you'll realize that once we have what we have over here, we have the Carey metric. Okay, Carey-Newman metric or Carey metric. You can have the charge, you can have the spin. Those we use that to calculate neutron mass, proton mass, all this. So that means we can use Hawking theory of black holes to calculate the proton mass, neutron mass, all this. Okay, so this is a very completed analytical solution, but it's an approximation. Okay, we can also do that to estimate black hole displace time. Okay, how much time it takes to radiate out all energies. That's where we need to recalculate the pion shelf life, all this. Okay, with the new equation, when you don't have a spin or you don't have a charge, but that's not close to reality. In the reality, you need to use the Carey metric, not the Schwarzschild solution. Use the Carey to calculate with charge, okay, with spin, okay. But we have a new equation now. We can do the same thing to replace the Einstein's Carey metric, but we don't present the solution over here. It's more complicated than the traditional Carey metric, okay? Because the new self-interacting field equation has a potential term. It makes it nonlinear. How many particles being created, how much possibilities, that's beyond my personal mathematics. That's why I'm putting out these videos for people to say, hey, now we have a new equation. Let's compare from the Carey metric, okay, of the general relativity and the self-interacting general relativity. We have two versions. We have Einstein's, we have new ones. But the beauty of that is we have two solutions. Now we can use this new field equation to study strong interaction and elemental particles. Okay, so basically we have a new equation for all elemental particle physics. Okay, so this is Robertson-Walker metric. Okay, it's self-interacting. Okay, so now what we have, we have this Robertson-Walker metric. Okay, that's the universe, cosmology standard model for cosmology, okay? That's a metric. We're going to see what this extra term does, okay? Because at this current cosmology, we found not enough matter to close the universe, okay? No matter what you count the extra stars, we're still one order away, or we may have only a few percent of the matter to be able to make the universe close. In our self-interacting general relativity, okay, self-interacting general relativity, we don't have that issue because we have a boundary, we have the gravitational constant varies, okay. For simplicity of this video, I want to see these terms, okay, because in the previous Schwarzschild metric, we see this term, okay, give us two solutions. Now what we want to do is, in this Robertson-Walker metric, this is equals delta mu nu, that's replaced to general relativity, okay, but we have an extra term, and this term is not zero, okay, we see that this is not zero. So we will see that what we have is an extra term. We still using the difference tensor to do that, okay. What we have is, in Einstein's general relativity, you don't have this term. After we define a difference tensor, we found that this is a scalar field, okay. Why I'm keep emphasis on this scalar field part, where Einstein left out, because this will bring us the quantum mechanics into the general relativity, okay. So general relativity and or gravitation, strong interaction and quantum interaction, they are all in the same equation, okay. So this term, it's the origin of quantum mechanics. We see that this term, it's a scalar part which has the potential the same as quantum mechanics, okay. So now we define something like that, okay. The only extra term, where it's this one, okay. I put it in red, okay, over here. So that's a difference between the self-interaction general relativity and the normal Einstein's general relativity, okay. That's what we see. I put it in red. We have an extra term, okay. So that's what we have, the RR term, okay. So this is what we have, okay. What's interesting that Einstein's, this is plus sign. In the self-interacting field theory, because of the extra term, the scalar term where Einstein left out from his general relativity, that contributes that Einstein's is supposed to be, this is positive r dot square. That means in order for the universe to be closed, k has to be positive 1, okay. So, but we see that in order for this equation to be true, k has to be positive, because this is negative. This is positive. If k is not positive, we're in trouble, because k has to be positive. Otherwise, this equation cannot be correct. But in Einstein's, because this is positive, Einstein's, this is positive r squared, okay? That's positive r squared. That's Einstein's. That's Einstein's, it's r squared, okay? So see that r dot squared. That's Einstein's general relativity, okay? In the self-interacting, this became minus. That's forced the k to be 1. Means the Robertson-Walker metric, if k equals 1, positive 1, k can only k equals 0, 1, or minus 1, okay? If k equals minus 1, the universe is open. K equals 0, it's on the boundary between, okay? K equal positive 1, that means it's closed, okay? So now what we see that the universe now it's closed under self-interacting field theory. I mean, this is, if we go back to the complete self-interacting general relativity, G has to be reintegrated, okay? For the simplicity to comparison, we didn't integrate over G. If we integrate over G on the boundary, the potential equals 0, so universe is automatically closed. Even without that, universe still closed. Now in the Einstein's general relativity, this is plus sign, okay? So that means rho has to be bigger. Now what we see that we reverse that sign, okay? The higher the Hubble constant, the less matter we need to close the universe. That means if the universe is expanded very fast, that means we're stopped fast, okay? So this is now, we don't have the philosophic trouble where the universe is just boom, okay, gone, okay? Now the universe can oscillate. We know why, because in the self-interacting field theory, the universe or the nuclei, they're the same, okay? Because our protons survived. That means these were oscillating, okay? So philosophically, this is more interesting. What we have over here, we see that the two solutions of the traditional Einstein's general relativity and the self-interacting relativity, after we rewrite Einstein's general relativity in order to bring the scalar field in, where Brandstad also did that, okay, but in a different way. So this is why I think it's interesting to do this. There are a lot more we can do. If we start integrating over G, can do the nucleon or proton or whatever other elemental particle, because the same equation can be used for the strong interaction, okay? So in summary, in both these solutions, their extra term give new physics to the Einstein's field equations. If we consider the potential tensor, there will be interesting features, okay? We'll come back to this in the future videos if we start talking about particle physics and we go using computer to do the nonlinear modeling of the nucleon reactions or elemental particle behaviors. We will see quantum mechanics. We will see more interesting properties, okay? So in the next video, we're going to do a summary of all the videos, and we think it's a gateway to the grand unification theory. Possibly we can put strong interaction, quantum interaction, gravitation into the same equation. If we can see that wave, then the wave propagates. How it propagates, we know the electromagnetic wave, okay? That's everybody's familiar. Now if we can design a signal where how the SQG wave moves in our nature, how it propagates, I mean, it's a new physics will be reviewed, okay? Thank you.